Okay, hopefully now it's working. Is it good now? Okay, fantastic. Very good. So I want to touch on the, do the lecture. And then I wanted to touch on the homework. So maybe I'll go in that order. Okay. Here we go. So today we're going to do take a step back and try to look at how we understand visual forms from the point of view of perception. So we're not going to go very deep in the biology and the neuroscience, but what we want to understand what works for visualizations and what doesn't. And there are a number of things that you may want to have in mind when you create a visualization so that you leverage that information. And then we're going to look at the scales and the axes. So probably you've seen in the homework that if you want to do a full graphic with D3, it's not just the data join that is already verbose enough, but then you need to do by hand all these little bits to create axes with labels and so on. And obviously, D3 has some tools to help you out with that. And those are the scales and axes. So we're going to see how you do that in D3 in the proper way. It's not something that you want to use for this homework. That's why I'm asking that you just do it minimalistic. And if you really want to put an axis, just make it as simple as possible with a line. All right, so we go. So to start with, obviously, all the information that we're getting is coming through our eyes, and there are things that we can see, typically what is in the visible spectrums. Everything else we don't have a clue about unless we use a sensor. So you can have infrared cameras that are going to allow you to see information in this bandwidth. And you see that we're typically be able to assimilate information through light between 400 and 700 nanometer wavelengths. And that goes for, this is the typical spectrum of colors of light that you are able to perceive. Now, eventually, we'll need to see if this is just in the light or if these colors are coming from somewhere else. Because light is just an electromagnetic wave. And so you can think that there is no real color associated with it. So it's really the way our biological sensors are built that allow you to associate colors with different wavelengths. And that has a number of implications for visualization. So here is an effect. Probably you'll see better on the screen than here. The more light, the less it's obvious. So here we have just two colors, and it looks like the red is kind of higher than the blue. So is that coming from the way the picture is set up, or is it coming from somewhere else? So the answer I'm going to give it to you is that it's coming from your brain, and or from your eyes. So those are the two possible possibilities, because the picture is not doctored in any way. And here you see that if we change the background, it's exactly the same picture with a different background, then the effect is gone. So there is something that is going on there that we're going to try to explain. So it has to do basically with the sensors that we're gifted with, that are the eyes, that take in some light, and they work like a photographic camera with some type of lens in front. And what the lens does is that it makes so that the ray of light that are coming in are going to converge somewhere towards the back. That is where we have most sensors that are useful for seeing in the retina. And as you can see in the picture there that I've drawn with different colors, the way the light rays are bent, I'm familiar with the prism, with the same effect, depends on the wavelengths. And so the blue wavelength is going to hit a little bit in front of the red one, and that explains the picture that we've seen before. So here already we see that you remember we said that we have gigabyte worth of information coming into the eyes. but this is one first type of distortion that happens that is due to the way we actually perceive light. So we're going to see a little bit more about perception and what happens with this visual information is coming in. So I mentioned that the rays in the previous picture, as you've seen, they all go in a certain region in the back of the eye, and that's ensured by the fact that this lens here is going to focus during coming light beams. And the reason is that that most of the sensitive, light-sensitive cells that we have in the eye are in this region right behind the cell on the retina. We do have elsewhere, but not as many, and not as good as those that we have there. And so the resolution changes as you go out. You might have noticed that on the sides, you see less well than right straight in front when you're fixating something. So this is the typical chart that you get when you go to see the eye doctor. And what it shows you is that these are the, if you fixate this point, these are the sizes of character that you can make up in terms of resolution. So you see that the wider you go, the coarser the resolution. So the letters need to be bigger so that you can see them in the same way, right? So right at the center, you see very, very well. And as you move to the side, you have less resolution. So in order to resolve the letters, you need to see them larger. Now, this is, as I said, related to the distribution of the sensors in the eye, where most rays end up going is the region is called the fovea. And you see that you have essentially two types of detectors. You might remember this from biology class. From high school, the one is called the rods, and the other one is called the cones. And you see that the resolution of the cones here is much higher, close to the fovea, which means that these are a better capability at resolving the visual information than the rods. So the cones are higher resolution sensors than the rods, and they're essentially you see a few degrees, 20 degrees, 10 degrees, 10 around the fovea. There is this artifact here that you see that is called the blind spot. This is where all these nerves, all the cells that are in the retina, that is here the red area, go out of the socket of the eye, go to the brain, eventually to ensure that you understand and you actually see. Because this, there is no information that goes to the brain, and you don't see through your, the light comes in through your eyes, but you see through your brain. If that makes sense. So these are cells, and they have this nerve ramification that goes to the brain here, going out, that transport the visual information. So each cell is going to say, I'm seeing a little bit of blue here, or a little bit of red, and then this goes to the brain that integrates that information. So right where all the nerve fibers that come out of the cells go to the brain, you have this area that doesn't have sensors, and therefore you have a blind spot. Now, the blind spot, you don't see it unless you do a simple experiment where you stare at a point and you have another point that is not far away from it, and you move closer, and at some point, one of the points will disappear because it goes through this region. So you don't see it, but it's there. Even if you close one eye, you don't see it. And the reason is simple: is that the brain is filling in the blanks. Right? So there is some processing that is done in here, the visual information, and then there is a lot of processing that is done back in the brain. And we're going to see how these processes work so that we understand what visual information is easier to assimilate and which one is not. Now, because we only see in a given region that is centered around the direction of gaze, what we do is that we keep moving our eyes around all the time, and that's involuntary movements normally, and those are called saccades. So you always move. There is always a little bit of jitter in your eyes. They move a little bit very fast. The eyeballs have muscles that are able to allow for this, and it's some of the fastest movements that you have in the human body. You see there 900 degrees per second. That's quite fast. Those are rotational movements, obviously, because the eye moves in the eye socket. And that's good enough to help you out understand very locally what is the information. But then if you're looking at a larger object, such as a face, you end up doing larger movements. And you tend to do them in some type of pattern that is guided by the brain. So here the brain gets some information, and that tells you, oh, let me see this other part of the scene. And as you scan around, then you get a better understanding of what is it that you're looking at. So this is typically what happens with recognizing faces. So you tend to focus here, as you can see, on the eyes, the mouth, those features, less on the hair, and that's because those might change. And so people have looked at those things over time with doing neuroscience research, and they have learned quite a bit in terms of how this influences the display of information. So we're going to look at that. Each time you stop moving and you focus on one area, then this is called a fixation. That is, you take in information that is very local. And as I was saying, that depends those fixation, whether the location here is the face, so you can stop in the eyes, but it's a different object, the pattern is going to be different. So the brain, it learns and it is going to focus on some latent features. So if you think in terms of a neural network, so those are latent features that the model is considering, the model that you build in your brain with real neurons to understand and recognize. Yeah. So hopefully you appreciate as we go the links between the biology and then the AI that we use today, because it's directly coming from there, right? So the models that we've built, neural networks, they're inspired. They're more than inspired. People were actually trying to mimic the brain with connection between neurons and information that is exchanged between those neurons, right? And up until the point where we understood that it would not work if you don't throw at it enough information, and if you don't put enough neurons in the system, then it was just a toy concept that was not really doing better than traditional machine learning, but now AI is just exploding because of that. And still there are some of the models are inspired by trying to mimic the brain. For instance, the LSTM model that has to do with memory was inspired by the way the memory mechanism works in the brain. So when we talk about visual information, you need to take into account the eye. And we've seen how the light rays are transformed into signals that end up eventually going to the brain. The old what people call the visual system is comprised of all of those pieces, including the eyes, the retina, the nerve connections that go to the brain, and the different areas in the brain where the information is processed. So essentially, visual information goes to the back of your brain in opposite direction of where the eyes are, opposite sides, sorry. And they go, they're typically called the areas P1 to P5. Yeah, the P5 is not shown here, but you see that you have sub areas that come into play, and then you have this thing here that is one particular construct where all the from one eye all the connections from the cells from one eye end up, and then they're kind of rooted to the visual cortex. And this is actually something that is explaining what happens when you move your eyes very fast, because then you're creating a lot of blur, and you don't want to send this back to the brain because you're creating unnecessary workload for it, because your sensors in the eyes cannot assimilate the information fast enough, and your brain cannot process it fast enough. And so this particular LGN here, that's his name, short name, you don't need to know it, but just know that what it does is that at some point is going to decide that this information that you're feeding me here is garbage. I'm not going to pass it on, so it just cuts it. And you're actually have a period of blank coming to the back of your brain. You don't see it because the brain interpolates things, right? So it knows what was happening before you were moving your eyes, and you move your eyes quite fast, so it can fill in the blanks for you. Yep. Now when you get to the interpretation of the signal is where the processing is happening in the virtual, in the visual areas of the neural cortex. And here you see an example of the things that can happen, where you have a picture and you can read it in different ways. And so your brain is going to try to explain what you see based on clues that he gathers. So it can be a rabbit with a mouse here, or it can be a bird with the beak on the other side, right? And so maybe it costs you to see it the first time, but then depending on where you look, your brain interprets it in different ways, right? So you have all these effects that come into play. Now this this flow that of information that we have discussed, where we say we go from the eye, we project on the retina, and then we go to the brain, is not a one-way flow. You're constantly working it out in the two directions, from the eye to the brain, and from the brain to the eye. So the brain can tell you, if you're looking at a face, go and move the eyes to the left eye and to the right eye. And that's something that you do very fast without thinking. So that's called subconscious. And that is the other side of the information processing, that it is going from the brain to back to the eye, right? And you use that when you're trying to process the information, focusing on it, meaning that you do this with attention. You're attentive to what is happening, and therefore your brain power is basically working on a complete task. And the eyes are the sensors that are that can be configured to fetch the information in the best way. So right now you can see that this mechanism is the thing that you're using when you're looking at a graphic and trying to understand it, right? If you just look at any graphic, you're going to go and look at the labels on the axis to try to understand what the data are on each one of the axes. Then you're going to look and search in the graphic for the way the information is mapped. So either with points, with bars, with lines, right? And then you're going to integrate this information into your brain to understand what is trending and so on. So both they work in parallel, and they work on more and more refined version of the visual information that comes in. So at the level of the eye, you're going to see very simple things, such as directions of lines, and that's going to be very fast because there is no brain power involved. Right, so you can detect very quickly a line, and that's why we're using line for line charts. You can detect very quickly if one line is parallel to another one or not. This kind of things, and that is also related a little bit to the three attentive features that we've seen, I think, in the first week. The example where you have a display with one dot that is completely different from in color from all other dots that are in the display, and you can flash this for a second and tenth of a second, and you're going to know that there is a dot that is different. You are going even to know, we're going to see that there could be a number of dots. You won't know exactly the number, but you will get a good feel for the ballpark of how many there are. So these features that are low level, they get integrated as you move in. So this is at the level of a single detector. So single detector will see a part of a line. And again, the detectors are concrete things. They're the cones and the rods that we have in the eyes. Then in the retina, they're integrated so that you can actually see pieces of lines. And eventually they get put together, say, okay, this is the line chart that comprises the line that actually does the plot, right? And that's done in the brain, where there you use your knowledge to form object level representation at even a higher level. So this is just a table compare the two directions. The first one that is the bottom up or data driven, and then the other one that is the top down, where the brain drives. So it's higher level of information that are driving the information gathering process. So in terms of the bottom up, here we see the perception results, meaning that what you are able to perceive with your eyes is directly transformed by the phone and the ROS detectors into higher information. So this is where the integration in the retina happens, and eventually leading to the visual areas in the brain that further refine it into objects. This is used for knowledge and attention, and that obviously influences the perception. The top down is the other way around, as we explained. Yeah. So things that you're getting from the eyes are processed in the brain. You use your knowledge, what you've learned, that is stored in memory, to drive how you need to further investigate the visual. Okay, so all this process encapsulated into what people who do information visualization called visual queries. So these are folks that are going to tell you what is it best to do and how to represent some data visually. Okay, so this concept of visual query is basically how do you understand visual information using the visual system. And the way we do it is similar to how we just go about life, where we ask a question and we try to find the answer to the question, right? So here it's the question is going to be visual. So you do a visual query. If you want an analogy with databases, right? This is how you formulate your SQL query to get the information that you need. But the analogy stops there because there you're going one way, right? Unless you want to create a complex query that has subqueries, then you would just do a bottom-up approach, right? So yeah, we're going to go for a simple example to try to understand what these visual queries are. And here the question is, which photoreceptor is present in the photo? So if you're confronted with this and you have this picture, the first thing that you need to do is to be able to find what fovea is. You might not know what it is or how it's used, or even that this is part of the visual system in any way, but even without any background knowledge, you just take the clues from the question and you go and search this. So here, typically, we will try to find the fovea. Then, in order to understand what this represents here in the graphic, you need to understand the axis. So you will go and read here the axis in X and Y. And you will then probably follow this line because it's pointing you to the X-axis and to the region where we want to know which receptor is present, right? So, and then obviously you continue this way until you find out that the distribution for the cones is predominant. They're based on the blue lines, right? So when you think about creating a display for showing this information, right? So if this is the information you want to communicate, then you want to optimize it so that these queries are going to be resolved as quickly as possible. You don't want people to go and you don't put fovea in the picture, then there is no way to resolve this query. Yeah. So the first thing is to make sure that the information is there so that people can actually resolve it. And the second thing is to do it so that it's optimized. It means that the people don't need to spend 3 hours trying to find that out, right? So in this picture, I would say that this is good for resolving the square, for knowing where the blind spot is located, and then which type of sensor they are in the eyes, based on their angle from the center of where the center of the eye. Another thing that is good for is that it gives you an insight into the data. If you want to know what the actual counts are, then you can read it on the y-axis, and the grid lines are there to allow you to read to get a good count of the maxima, right? Now, if only the maxima is the thing that you want to communicate, maybe you don't need all of this. You can just kind of take the picture with the actual number, right? And that goes to the idea of doing minimal visualizations. Because in a minimalistic visualization, then you only put the things that people need to resolve to answer the query, the visual query. And so there is no chance that they're going to spend their time looking at other stuff that is not useful to them. Yeah. Yeah. So now this process here is going in the two ways, right? So you go from fovea, then you need to go. So you found a clue. So now you need to interpret this clue. So you need to go and look somewhere else, and the brain is driving this process, right? So it's both top down and bottom up. So you'll see in the required reading that these are the definitions that Pauline Ware gives us. So maybe I can read them and we can try to explain the words. So a visual query is a pattern cognitively specified. So what does it mean? Cognitively specified. So it means that you specify it in your head. Okay, so in this case, I had written the query. When you look at a graphic to search for something, nobody writes it for you. You create it in your head, and you say, okay, I'm trying to look here for where the fovea is located in with respect to the center of the eye. And that's your query, right? And this you specify it in your head. Your brain makes it up and directs your eyes to the x-axis. So this means also that because it's cognitively specified, you can also close your eyes and you can specify it, right, without looking at the display. So in some instances, you say you're using a display while driving, right? You need to resolve these queries offline because at the same time you need to drive, so you cannot look at the display all the time. So you take a look at the display, then you formulate your query in your head. You resolve it in your head based on what you remember. If you cannot resolve it because you don't remember it, then you go look at the display and you search, right? So the cognitively here is the offline part, right? That if found in the display will contribute to the solution of a problem. So here we have also this idea of the goal of a visualization that needs to be there. Then there is another one that is visual thinking consists of a series of acts of attention, driving eye movements and tuning our pattern finding circuits. So here, the only thing that is saying that we didn't discuss is this tuning the pattern finding. So when you're looking for something, you're just not staring at the display, you're actually thinking about it. You have an idea of what you want to look for that is driven by the brain, and that's the way you tune it, right? And so this you can do it online. Some of the tuning is, so you have some of the example of the bistable picture there that we saw. So sometimes you have this picture of objects that you cannot make sense of, but as soon as somebody tells you, oh, this is a dog, then your brain is tuned to that pattern. And the next time you see the picture, you're going to see right away that it's a dog, okay? So that the tuning there is in that sense. Yeah, so the implication in terms of design is I think we discussed this, is carefully craft visualization to optimize visual queries. Okay, so each time you put something on a display, you want it to be able to achieve the goals that you're expecting. So now for those who are offline, probably you can play it, but from the interactive slides on the website. So here I'm going to maybe cut the video, cut the sound, sorry, and play it. Yeah. I don't know. Okay, so this is some work that has been done on attention. So we understand what attention is. And there is this thing that is called attentional blindness. So we're going to see what it is. So what they did is look at how people interpret MRI images for finding cancer cells or lesions. And they took those people that are experts, so that their visual system is trained and is tuned to find the lesions, and they're very good at that. But then they put stuff in there that they don't expect to see. Yeah, and they counted how many times you see it was the little gorilla there. How many times they missed the gorilla? Even though the gorilla, anybody would see the gorilla if you're not trained, because you would just look for a pattern that makes sense. But these guys, they're using all their brain power to look for lesions, and they know what a lesion looks like, and it doesn't look like a gorilla. And so their brain is just cutting out the gorilla information whenever it sees it because it's irrelevant. Okay, and that's called inattentional blindness. And the repercussion in terms of graphic displays is that if you say you do, there are different ones, but I guess the most compelling one is that if you want to point to somebody with an animated an animation in the display, and they're using their brain power to look at something else in the display, they're not going to see whatever information you're trying to communicate there, right? So don't, and that has also to obviously to do a little bit with the fact that as we use attention, our field of view is kind of narrow. So if we don't look at the right place, we don't see it, right? But with animation, you see very well things that are moving even in the periphery, unless your brain is overloaded with another task, right? So the visual queries, sometimes it's difficult to make sure that here, this one I can do it like this. Let's see if we can count the ball there. I don't know if they want you to count for the black team and then for the white team at the same time. Maybe. Six is basic. Everybody got it? Did you see the gorilla? It's a large display, and then you're kind of okay. We just talked about a gorilla, so you kind of prime, but not everybody saw it. And here you can see also the color of the background changed, and that probably you didn't see it, right? But it's the background, right? It's the whole thing that is changing color, and you didn't see it, right? So here is the replay. You see it's drastic, yeah. And that's just because you're focusing your brain on one task. Your visual system is moving around trying to track the ball, and if you really do that, then you're going to miss things that might be important. Okay. Oh. Okay. And to kill the notifications here, and okay, I want this button here. Okay. Okay. So the thing that is there is called an inattentional blindness. So you become blind because you don't have enough attention to go around. Okay, so you're using it for something else. So there you see different characteristics that define it. So it's a failure to detect an unexpected stimulus that is fully visible. The gorilla. Limited attention allows to focus on one thing at the time. That's true. You cannot drive and text or you can until fatigue happens. And the brain is really responsible for focusing what is it that you're going to see as visual information, because that's driven in the top down, bottom up, sorry, direction. So I think I discussed some of the implication for design, but let's go through it. So these I picked from the book, both from Ware and Cairo. So for designer, it is important to know what kind of visual information the brain can process efficiently. So some of it today, but we'll see this in more detail as we go on. Be aware of inattentional blindness. Never show simultaneous animation on different parts of the screen. Okay. This is because if I look at this one, and this is too attention grabbing, then I won't see anything about the other. Do not use too many competing stimuli. So that means that when you use color, for instance, and the color is different from everything else in the display, but that makes sense for highlighting. But if you start overdoing it, then you have a lot of red color all over the place, and then it's useless, right? So you're asking people to just pay attention here, and here, and you don't. You're slowing down the visual querying process. Filling graphic with object color and pure accent tones disorients the user. So this is a journalist that tells you that it's obviously a good advice to follow. Okay, let me move again the zoom windows from the way. 49. Yeah, maybe we do a quick break before we start the scales, so that we start right on time of the hour and we even split. Okay. Yeah, give me a second because I just want, and then I'll be back to you. Okay, here we are. So I was saying, so the scales are one of the tools that are going to allow you to cut on the code that you write. So you don't need to do all the math on the side there in the D3 function each time you want to place something. And also they're going to be useful for configuring the axis, because it's basically the same thing. It's how do you map the data to the graphic. So for you using the scales for setting up the height of the bars and so on, based on the data, right? And at the same time, you're using it for visualizing the scale, and that is done through the axis. That's what the axis are. It's just a visualization of the scale, right? That's it. I'm going to go there. Okay, so this is a plotly thingy there, but my point, I don't know why that is not at the here. Can I move? Okay. So you have other elements such as the legend, etc. So this we're going to see. We're going to see later. But for the moment, we're concentrating on axes, tick marks, grid lines, and how do you realize this with Stephen? So some of these, so here the legend is really this part of the graphic. So I'm not referring to title. This is the title of the graphic. But the legend here comprises the title. The keys are the colors here that thumbnails that are showing, and then the key labels are whatever text is associated to the category here, right? So those, if you want to do that, now you know how to do that. With D3, you can do the insert append, select append. If you put your keys into an array with key labels, you can do a data join with that, and you know how to do this very quickly, right? With SVG. I think that there are a couple of libraries that are out there that can do the same. Because if you want to make them nicer with a border around and so on, then it gets complicated. So the type of scales, not surprisingly, they mimic the type of data that we've seen: the nominal, the ordinal, interval, and ratio. And obviously, you need to start from your data to realize that. So here I've done code that I'm not asking you to do. For the simple reason you know how to do it, but it's just easy. So I did this simple graphic here with the 3 bars, and I put some axes with tick marks and labels, and tick labels. And this is the code that you need to do if you do insert append. Okay. So I select. So this is the data join of the rectangle. So this is the data join into bars. This is a data join that is placing labels. Yeah, I think the labels for the axis and so on. This is adding the lines. So it's a lot of code, and then you have to do all this little math here to configure and make the space for these things, because otherwise your bars would start here, and that's kind of tricky to do. So obviously D3 has some functionality to help you out. So the first one is the scale, and then there are the things that are called the axes. So the axes are again realization of a scale. So not surprisingly, you will see that you first create the scale and then you pass it on to an axis, and you say, axis, this is my scale. Draw yourself. Okay. So going back to the scales, it is just a linear mapping. We said that most of the time that's what you use between the data and what you have on the page, right? So what you have on the page is called the representation, and what you have in your data is called data. And so the wording from D3 is that you go from the domain of the data to the range for the representation. Okay, that's this is the y, and this is the x of the linear function that you're using. So how do you specify this? So the domain, obviously, it's a range of data that you need to find. If you do a linear mapping, you need to find what is the minimum and the maximum. So D3 has two functions that allow you to do this. So you can specify the domain to find your smallest data point in your data and what is the larger one. So here it's 10 and 100. Nothing special to that. And you see that you pass data. So this you can understand that they're just array manipulation functions, right? But they come handy because by stock, you would need to create a function just for that, which is a minute for the for each, but you do this so often in D3 that there is a functionality that is built in. So once you, so this is the way you specify the domain. In the range, this it's a given because the range has to do with the size of your SVG, right? So you size your SVG and then you say that the range that I have in X and Y is 100 and 400. And here are the scales materialized with the domain. This is the range of our data, and this is what we have to, the space that we have to plot it. Okay, and what we want to map is the stand that goes to 0 and this 100 that goes to 500. Don't ask me why it's 500. My example has a 400 because it's a mistake. So you can do linear scales, but you can do also all sorts of other scales depending on the data. For instance, if you have time, then you want to create an axis for these dates. D3 allows you that. They have a time scale. Another one that is often used is the logarithmic scale, when the range of your data is such that you would not see, you know, the whole range into the graphic. You will be able to resolve it. Then you can try to use a log scale, and that was my original example at the beginning. So all of these, the rest here we can talk about it when we talk about. So these have more to do with statistics and if you want to do box plots and this kind of thing. So yeah, those that I have underlined here are those that we tend to use most often. All of these are part of continuous scale because the data is continuous, and that's it. And so yeah. Then if you have bar charts, for instance, then you need a different scale. You need a scale that works with categorical data. And so there are different types here. There is the ordinal, where your labels have given order. You're going to say this is my first one, this is my second one, and you'll be able to specify a mapping to that. The band and then the point. So these are useful for doing two things that you've done. One is the bar chart, and this one is if you want to do the lollipop chart, this might be useful for that. Okay, so here are some quick examples on how you use them. These scales. So the simplest one is the linear scale that is good for continuous data. So here we have a data set that goes between values 100 and 150. So we get the domain with the min and the max, and we configure it. After we declare that we want to use a linear scale, and so this is the way you instantiate a linear scale. As I put there, this is a function that gets called. So our variable is a function, and this instantiates the linear scale, and then we configure it with the chaining syntax. So we set the domain and we set the range. The range being, again, what is the space that you have to map to. And then you can just go and use the scale with X. Now, how do you test if you want to try this out quickly? How do you do it? Can I do it in the page here? I don't know why I have an error there, but we have 404. Okay, good for the server. Okay, so I can do this if I have D3, right? Okay, so my guess is that I have D3 because I put this okay, so X of 100. Okay. X of, what is it there? 125. 125. Okay. You see my example is bogus. Yeah, because this is we didn't configure it. So here we're getting probably the default for the scale. That is between 0 and 100, and so these are correct answers. So if we want to actually configure it with the data set, we need to execute all of this. I don't know if it's going to like my comments there. So, yeah, it looks like yes. Okay, and then if we do X of 125, we get 50, which is correct. Okay, so that's another reason why I made the slides interactive, so you can go and play with them. Because D3 is in there for all the D3 examples. Let me close this thing here. Okay. Okay, so now the way I'm debugging this, you can do it interactively here. If you have a page that is set up with the browser sync there, you can do the same, right? In the command line. If your scale you think is not doing what you expect it to do, you can go and debug it in this way. The scale time here is the same. So the only difficulty obviously is that you need to specify the time in some way. So there are libraries. We're going to see this in the lab that you can use. I think we're going to use Day.js. There is another one that is called Moment that are popular. That allows you to specify dates and then do operations on dates, number of days between this date and this other date, for instance. JavaScript vanilla comes stock with the date class. So this is how we instantiate it. So here I create a new date for 2018, so year, months, and date. Okay. So here I'm using the scale time. So this is a linear mapping. This time, unless we're going relativistic, is linear. That's the assumption you can make. And so the domain is related to the data because we're using a scale time, then we can use the dates here for the domain. The min and the max will probably not work because the min and the max they're done to work on arrays. I don't think that we'll understand the dates. Sorry, arrays of numbers. They will not understand what the date object is. So that's why sometimes you need to get a third-party library like the DGX and the moment. If you have a lot of dates and you want to know which one is the minimum, the first in time, then that's a good way. Yeah, so obviously when you call the scale, you need to pass it a date object because this is a time scale and they understand this is date object. So here you see an example. I'm asking for the date for this particular date. Yeah, this is just if you want to have the current time. This returns a Unix timestamp, more or less. You can call date.now. Right? Sorry?
Range 0 to the range.
Oh, the range.
Yeah.
So again, the range is the space that you want to map to. So this is defined in your graphic, right? So here, say if I want to do a time scale, and I want my axis to be 960 pixels, starting at 0 in the SVG. Yeah, it's all the time the same thing. So go back to this graphic. Yeah. So the range again here is the page and the size of the SVG that you want to plot it to. The input is your data, right? That you want to put in the graphic. Scale time. Okay, scale log. Not much to say except that you go from scale linear to scale log, and then you can pretty much use the same than you had before. The scale ordinal here we're mapping to the discrete domain. So you can go and play around with those so that you see how they work. But those with the scale ordinal we rarely use. The one that we use a lot and that you need to learn is the scale band, because as you can see, these are bar charts. And so what it does is that it helps you to do all this small calculation that you've been doing for creating the bar charts with the gap between the bars, etc. So it's all set up for you. You just specify what gap you want, and then it's going to plot it. Okay. So the way it works is scale band. So the domain obviously is discrete. So here, these are your labels, and you see that they're labels, they're strings. And these are not numbers, right? And we want to map those numbers in this range with the scale band. So what the scale band does is that it's going to tell you which is the bandwidth of your bars that you need to plot them and where they should start. Okay, so the only thing that you need to tell to the plotting routine to D3 is here is my bandwidth. Start it here and you're done. Right? So you configure it still with the changing syntax. So here, for instance, if you don't put anything, you're going to get the defaults. But here we're setting a padding inner, that is the space between the bars. You have a padding outer, that is the space between the leftmost and rightmost bars. Okay? If you want to have some space there. And all of these are always in pixels. And you see that the defaults inner padding in 0, 1, the default is 0. Yeah, and then you get this number that we're going to see how to use in the lab to build the bars that basically, yeah, that cuts a lot of the tedious calculation. Sometimes you want to do similar to the lollipop chart, and then you need to center the data with the graphic. In that case, the scale band is a better thing to use. We just don't care about bandwidth. So it's similar to the scale band, but without the bandwidth. And you see that the steps here are the equivalent of the inner padding. They have a different formula here for all the padding by default, but that's about the same. Okay. Okay. So here I put boilerplate code for a reason is that hopefully you get the point that you don't want to reinvent the data joint, and this is not say, well, yeah, it's the same declarative, sorry, same syntax that we're using with the data join there, where we're saying what we want to do, we don't say how, and you don't want to reinvent it. So usually this is the pattern that you want to use. Now it's more of a series of operations than the actual data join, as you can see, but that's basically the layout. The layout is natural. Again, I mean, this is obvious, is because to create an axis, you need to know of a scale. So the axis is configured by a scale. So you start by creating the scale. Okay. So here we're just creating an SVG and we're setting some size. Then we create a scale. Then we create an axis. So here I'm creating what is called an axis left. We're going to see in a second what that means. And this is an object that then you can configure and ask it to draw itself. And you see that here when we create it, we pass in the scale. Yeah. So what it means is that as soon as we have defined the scale, you have some defaults for the axis that here in this case look like this. And this is already a lot of work for you without doing anything. The only thing that you need to do is append it to the SVG. Now the way you append it is with the group, for the simple reason that the way week3 realizes the axis is with different elements that are put together under a group. So there is no hierarchy in SVG, but you can say these elements are grouped together. So if you look at Xscape, you can select multiple pieces of graphics, and then there is a group by, right? And that group then is put under a transformation that you can just move around at once, right? So here is the same concept. You want to put all these elements together because the axis is created in a standard place by default, and probably that's not where you want it in the graphic, right? I don't know what are the defaults. My guess is 0, 0 or 10, 10, something like this. So what 0, 0. So otherwise we will not know. So if you want to move it to 50, 50, then you need to translate it in this way. Okay. So then, again, these are attributes of the group element, and so we're just setting the transform attribute equal translate 50, 50. Okay. So that's just plain HTML code there that we're calling. Yes.
Normally it would be like the first at the top and the bottom.
For the moment, we're not reversing anything using the 0 is at the top. The axis. Yeah. So yeah, the only thing that is peculiar in here is this thing at the end here that is dot call. Okay. So this is because this object is a function. The axis is a function, and you can ask the axis to draw itself at this position, but you need to call the function. Okay, so here we just create it, and nothing is done. As soon as you append it, here we're appending the group. We're not appending the axis. Yeah. So if you don't put this, then you have a group that you move at 50, 50, and because there is nothing inside the group, you won't see anything. Yeah. So we still need to say at this position we want to realize the axis. And so this call, all it's doing is calling this function. Yeah. And this function knows how to draw itself wherever it is placed. That's all it is, okay? Don't get confused by the call. All it's doing is call execute this function. That's what it means in D3 speak. Okay, so the axes, you have essentially 4 types, and they're called after where the tick marks and the labels are placed on the tick marks. So axis left, it means that things are on the left of the axis. This is the axis left, this is the axis right, this is the bottom, this is the top. Okay. Most of the time you want to use the left and bottom. Okay, so make sure that you remember that, don't get confused about it. And the way to remember it is that it doesn't, here the one that is on the left, right, you don't want the area inside here to be used for the labels, you need to be on the left of it. Yeah, it doesn't make sense to call it otherwise. Yeah, so some more code here. So if you want to style these things, so it's impractical now that we're doing this. So I'm setting up the axes, and then you know, you don't want to go and you overuse the chaining syntax with for each one of the axes, because most of the time your axes are going to look the same. So you want the same settings, so you probably want to pass them. And so the way this is done is by using CSS. That's the best way to do it. And then you set the class, either with attribute class or class, whatever the class name, true or false, true if you want to add it. Yeah, so if you look at the SVG, it tells you basically, so this you want invented. Okay, so it's boilerplate, because you need to go and copy it, or read the documentation and find the examples. Because this you cannot know it. And the reason is that here you see that it's using path. The path element is an SVG element that is used for doing everything, including the line and the tick marks. Okay, as opposed to just using lines. And this is done because sometimes you don't want a line for an axis, but you want something that is a spiral or something crazy, and D3 allows you to do that with the path. Okay, so yeah. So here, if we look at this, we like this, we understand quickly. So we say that every path that is in the SVG04, we want the scope to be blue. Then the one that has a class of dash axis, we want to have the scope orange with dash array of 5 pixels by 5 pixels is this one. And you see that it's classed somewhere here, right? And it's I'm calling the axis with underscore L for the left to make sure that I'm remembering which one it is, and the B is for the bottom. Yeah. Remember, the space is something that's inside something. Okay. I think I need to get a break because I'm starting to have trouble talking. Okay. Boilerplate for axis labels and grid lines. So again, this is example you want to invent it. There is nothing spatial in D3 to do these things. So you just need to CSS it. The grid lines, you basically need to do lines with staple position, and you need to add them one by one. In maps, there is, we're going to see when we do the maps with D3. Those are called graticule, and you have functionality to say just draw a graticule for me. And probably there is some third node library that allows you to go extend if it's not already in D3 to do grid lines that match the axis, but I'm not aware of it. Okay, so this is the last slide, and this is it the last? I think there is another one. Yeah, okay. The last slide of content here is about the margin convention. So you were mentioning earlier, how do I do to ensure that I don't need to think all the time about this y-axis that is towards the bottom, when really I want to start plotting with the origin on the lower left. So there is nothing special that D3 does about that, but there is a margin convention that is a kind of another recipe. So take it as boilerplate again. That allows you to set up the SVG with transformation so that you make D3 believe that it is working with an SVG where the origin is lower left, and the y-axis is oriented to the top. And where this is inside the SVG, so you have space for the actual axis labels, etc. on the side. Yeah. So the pattern is right there. So you don't invent it, you just copy and paste it and configure it so it matches what you need to do. So you see that the top there is just setting up some variables. So you set up the margin, which is the area that you want on the side. So you make all this padding all around. Then from that you compute the width and the height of the graphic, given the width and the height of the SVG. And then you need to tell D3 that this is its drawing area. Okay. So this is a trick basically by using the group with a transformation that moves the origin down here and flip the axis as you would expect. And then this is your new origin and axis. You just draw as if you were here. Okay. Yeah, I mean we can go for it, but it's basically what it is. Yeah, and those are what it does, right? As the padding inverts the y-axis, move the origin on the bottom left. Okay. Margin convention, again, remember what it is, and this is the first thing that you would do typically if you want to start drawing any chart. You would want to use this margin convention, unless it's something very simple with that you want to do. In that case, you don't bother, you do the math by hand. But this saves you a lot of brain power that you can use for doing other productive things. So I put together all these elements, the margin convention here, using the scales, and I did the same graph. Okay, all this code goes there, and in the pages you can inspect it if you want. But now you see that we're down with all of this to one page, when before we had more than two. And it's much more understandable in terms of what is it that we're doing, right? We just do the margin convention. Here we know clearly how much space we want around the graphic. We use a scale band for doing the bands, so we don't need to do much of the computation for the width, right? Yeah, here this weird idea I did it not to do the rest of the presentation. It's unique. So this is part of the market information, right? So setting up the drawing area. And then we do the data join with the rectangles. And here you see that the only thing that I need to say for the width is say x dot bandwidth. So this is the scale band that gives me the bandwidth. And I just pass it on as an attribute and pass to the width of the element, here the rectangle and the Anton. Yep, that's basically it. Okay. Yeah, that's it. If we have a bit of time, do we? 39. Yeah, we have 10 minutes. So I wanted to talk about the homework and the table. So, maybe. So this was the table. Okay, so in the homework, I'm asking that you do a table with the text, with some text. So how do you go about doing it? And I'm saying this for two reasons. One is I think it's a good way of understanding how the tree works and how you can use it. And the second one is that if you are working on the lab and it takes you too long to understand something, you shouldn't spend too much time on it. Use the Slack or show up at the office hours and try to get at least a good understanding of how to proceed. Okay, or just try to do it during the lab sessions, and if I still don't address the problems that you have, yeah, use the chat or anything else that you can use to communicate with me so that I can address it. So the table, this is the loading the CSV. Let me go to so for doing the table, you have I think 20 countries and the data for 50 countries, right? And so the first question is it's an HTML table. We did this in the lab, so you want to go and reuse that code, right? So there is no need to go reinvent it. I mean, unless you want to go and see how people do it differently. But then, yeah, I think that in this particular case is not very useful because there are not 20 ways to do it. So the problem here is that the data join, the core problem is that the data join works on arrays, right? And a table is actually not anything different than that, right? You can put it in an array fashion, but what forces us to use somehow a hierarchical data structure is the fact that we're trying to squeeze it into an HTML table, and the HTML table is hierarchical. You have the rows and you have the columns, and the columns have to be inside the rows. Right. So the pattern that we saw there for doing the data join with arrays of arrays is what B3 implements, and that is useful for doing hierarchical graphs. And we're kind of twisting it to do a table. Okay, so that seems to be a good way to do it. However, when you try to implement it, and basically is this code, right? So you just need to cut and paste this. So how do you make this work? With what is asked. So what is asked is that you load the data in CSV, and then you use the D3 data join, right? Now, the problem that you see very quickly is one that the data here is in the form of an array of arrays, while if you use d3.csv, what we've seen is that you get this array of objects. Okay. So anyhow, even before you get there, you don't waste too much time. You implement. You can implement both things. The d3.csv that loads your data. And then instead of doing the plot, you just take and cut and paste this code in the .then function. So you make sure that this code is working. Okay, because you don't want to address two programs at the same time. So now the second problem that you face is trying to squeeze what you get with d3.csv, that is basically returned here, into this pattern where we have an array of arrays, right? And so we're discussing about this. When was it? Sunday or yesterday? I don't know. Yesterday. And yeah, I had a bit of brain fog yesterday. Not COVID related, because I've been working all day. So you see you don't want to just jump the gun and as I did and find what is the best solution. So you have but you really want to think about what D3 gives you and how it's best to use it. So the data join is complicated, right? So you could think about modifying the data join, and that's what we try to do. And we find out the way to do it, but it's complicated because if we have an array of objects, then there is no hierarchy. So we can add the rows, but then we need to do a select and append on the rows for adding the columns based on the data, and which we cannot do with the data join. So it's significantly more work than to try to use the pattern and to change the data to an array of arrays. And then what we try is say, okay, let's change the data to an array of arrays, which is straightforward. All you need to do is take your data of objects and turn it for each object. You turn it into an array where you get the keys and you get the values for each one of the keys, and you put them into the array, and that's what you're done. And you do this with a for each loop and a push. That is not unlike the Python, right? Push and pull. So that's quickly done. But then can somebody tell me why this is not using the D3 correctly? So here instead, so here I get the data that is an array of objects. Then I turn it into an array of arrays, and then I use our plotting code for the table, and I'm all happy, right? But here there is something that I'm doing wrong. Can somebody see it? Or is it just me that had brain fog yesterday? So you remember that. So JSON, when you read, what is the difference between reading JSON and CSV? That CSV you get all strings, so you need to change them, right? So where do we do that? Where do we change the strings to integer? Right there. But can you see what we're doing here? Can somebody tell me what this is doing? Yeah, that's fine for this. So this is the casting. But what this return is doing? It returns an object. So we're creating the object in the first place. Right? So we create the object, and then we change it into an array here. right? So you better just create just return an array here of these, and you're done, and you use it. Is that clear? I guess that most of you have done it already, but it took me a while to get it. Yes, no? Yeah, exactly. Yeah, the array is the square bracket. You put the square bracket, and then you don't need the key values. You just pass the values. You do this, and then you get an array of arrays, and you just reuse the code that we have in the lab. Okay. Okay, I think we're 1 minute off, but if yeah, this is all I think for this week. Yeah, the homework for next week, the A5. A5 is basically A4 with the accents. And I think I forgot to put the margin conventions, but I'll post in Slack. Yeah. Yeah. So the header equals to the code is not the header not to CH. So let that repeat.
Yeah, I know, that's what I. But this is the basic.
Let's go outside.
Yeah.